The purpose of this video is to explain the difference between a probability distribution on the one hand and on the other hand a likelihood function. And I'm going to do that by example, and it's going to be an example if we have a large academic department and we're interested in gender balance, and we do a survey and discover that we have 22 individuals who self-identify as females and 8 individuals who identify as not females. So I want some sort of a binary dependent variable, and that's what I've got here. And what I'm trying to do is answer the question, is there an equal number of females and not females? Or another way to think about it is, if we think of pi as being the population parameter, the proportion of individuals who are female, is that equal to 0.5? And I'm going to examine this question in 2 different ways. First via a probability distribution, then via a likelihood function. And in doing so, I'm hoping I can get across this very important concept of a likelihood function. So let's begin trying to answer this question with a probability distribution. So what we're going to do is we're going to have a null hypothesis, and our null hypothesis is that pi is equal to 0.5. And then what we can do is we can use our binomial. Here's our binomial. And the way this is going to work is we're going to hold pi constant at 0.5, and we're going to vary the different values of y and see what effect that has on this value here. So what we're going to say is here's our null hypothesis. So what I've done here is just taken this equation here, n is equal to 30, pi is my null hypothesis of 0.5. This is a probability distribution. So this thing p at y is a function. And you plop in different values of y, and what comes out the other end is the probability that the random variable will take on that particular value of y when the experiment is actually done. So what we're going to do is we're going to hold pi constant at 0.5, and we're going to vary y. We're going to vary y starting from 0 females all the way up to 30 females. And we're going to calculate the probability of getting a particular number of females between 0 and 30. And we're going to plot that down here. So remember, pi is constant at 0.5. And on the horizontal axis, what we're doing on the horizontal axis is we're varying y, the number of females, so y goes from 0 females to 30 females. We're going to plug y into this formula. What comes out the other end is p of y, and that is what appears on the vertical axis. So if we come back to our question, do we have gender balance? Well, here's what we observed. We observed 22. So if we ask ourselves, okay, what's the probability? What's the probability if pi was really equal to 0.5 to get something as unbalanced as we observed? What's the probability of getting something way out here in this tail? And we can calculate that as equal to 0.00261. And so the typical way we do null hypothesis testing is, if we got a value that this low, we would reject the null hypothesis of equal gender balance in favor of an alternative hypothesis that there were in fact more females than males. So that's probability. And the key thing is that the parameter pi was kept constant at 0.5, the number of females varied, and we calculated P at Y for each one of those different combinations. Now what we're going to do with likelihood, we're going to flip that around. So now what we're going to do is we're going to hold Y constant at 22 females. Now we're going to vary pi, and we're going to calculate that function. So let's just do a couple of examples. Let's start off with an example of pi is equal to 0.4. So if we think of our binomial, it's going to be 30 over 22. So we're holding Y constant at 22. We're going to set pi is equal to 0.4, raised to 22, 0.6, raised to the 8, and that turns out to be 0.00017. Now we can change pi. That's the whole idea. We're going to hold Y constant and vary pi. Now we're going to change pi so that it equals 0.8, and what we'll get is 30 over 22. You see, we're holding the number of females constant at 22, but now we're varying pi, so it becomes 0.8 raised to that constant number of females, 22, times 0.2, constant number of females is 8, and that's going to give us a value of 0.11056. And we can reproduce that process over and over again. So again, we're holding the number of females constant at 22. We're taking this value of pi and we're varying it. And then what we're doing is we're calculating, in every case, P at Y, and that's what we see in this table. So here's our 0.4, gives us that, 0.8 gives us this. So if we look at these values, these are held as discrete values, but in reality, this pi thing, that's going to be a continuous variable. So we can plot it out as a continuous variable as shown here. So we're going to hold Y constant at 22. And then we're going to vary pi. Pi, the proportion of females in the population, is going to go from 0 to 1, and that's a continuous variable, and that's what's shown on the horizontal axis. So on the horizontal axis, we've got the proportion of females going from 0 to 1, and what's going on the vertical axis is P at Y. That's calculated as we showed here. Now, I'm calling this thing a likelihood. And that's a bit odd because it's really no different. It's still this P at Y. Why do I call it a likelihood? Well, the reason for calling it a likelihood is that when I go through my process, and again, let's remember what the process is. We're going to do P at Y is going to be equal to 30, choose 22, 30, choose 22, pi to 22, 1 minus pi, the 8th. We're holding pi constant, we're changing pi, excuse me, we're holding Y constant, we're getting this thing. But this thing here is not truly a probability. And what I mean by it being not being a true probability is I can compare that with a normal distribution. Here's my normal distribution, and if I take the total area under a normal distribution, that's equal to a value of 1.0. On the other hand, if I take the total area under this likelihood function, it's not 1.0. So these things are not true probabilities because they don't sum up to 1. So if that's the case, what do these things mean? Well, by themselves, they don't mean a heck of a lot because they're not probabilities. On the other hand, relative size of these things can be fairly informative. So if we look at our likelihood function, here's our likelihood function, And we can see that it's maximized here at a value of 0.733, which is equal to 22 over 30, which is not terribly surprising, because what this is telling us is, in the absence of any other information, the most likely estimate of the population parameter pi is obtained by the data, 22 out of 30 being females. But where this thing can become useful is looking at relative probabilities, or relative likelihoods, where we've got a relative likelihood of 0.163 associated with that 0.733, the 22 out of 30. But if we come down here, what's the likelihood associated with kind of a null hypothesis of 0.5? It's a much smaller value. And so the ratio of these two provides some pretty strong evidence that the proportion of females in the department is not equal to 0.5. And so just as a summary, here we've got this little figure, and what's written here is exactly the same as what's written here. The value on the y-axis is equal to blah, 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 blah. In the case of a probability distribution, we hold pi constant at 0.5, and we change the number of females. In contrast, with a likelihood function, we hold the data constant at 22 females, and we change the value of pi.